Everyone. All right, we're almost there. In one more day, we'll be able to say the word Galois in a definition, right? But we're not quite there. We've got a little bit more work to do. So let's see. Last time we had this sort of characterization of separability. So remember, separability, that corresponds to not having multiple roots, right? If we say that an extension is separable, if every element is separable, an element being separable means that it's minimal polynomial separable, and minimal polynomial being separable means that the minimal polynomial does not have multiple roots, right? Each of the roots that it has are distinct, or let's say are simple roots. Okay, and so then we had this theorem that characterized separability, right, which is this notion of polynomials not having multiple roots. It was characterized in terms of counting the number of extensions of a monomorphism, which is kind of a strange, I mean, it's not obvious, right? I mean, we went through the proofs, right? But it's not obvious at first glance why that would be true. Now, I mean, once you go through the proofs, you see, oh, okay, not having multiple roots allows you to keep track of how many extensions you have, right? Multiple roots would screw that up. Now, what we want to do is get a little deeper into this counting process. And so, or we're going to make use of this counting process to get further results about separability. So our first, and these are going to be, we're going to have a couple of corollaries. So corollary 4.4 is our first one. So if L equals K adjoin alpha 1 up through alpha n is a finite extension, of K, and this is going to look a little bit weird here, and each alpha I is separable over K adjoin alpha 1 up through alpha sub I minus 1. So when you write that down, make sure you get that subscript right there. So if alpha I is separable over K adjoin alpha 1 up through alpha I minus 1, all right, then, L over K is separable. So in some sense, what is this saying? If you can build L one adjoinment at a time using separable elements, right? Separable over the previous adjoinment, right? Then the overall extension is separable. Now, one thing to notice. Okay, so what does that mean when when I equals 1? Right. So we'll just say so when I equals 1, this means that alpha I is separable over K. Right, so that's our notation here. Okay, so for the proof, so first what I want to do is I'm going to multiply some minimal polynomials and create a big polynomial. So let's call it F. So let's let F equal the product. So this will be minimal polynomial of alpha 1 times the minimal polynomial of alpha 2 times minimal polynomial of alpha n, where these minimal polynomials are over K. So so these are minimal polynomials over K. Now this is by corollary what? 3.3. So by corollary 3.3, if we look at the splitting field, and I want to call it capital N, so the splitting field for capital N over k. This gives us a normal extension. In fact, a normal closure. So splitting field for n gives us a normal closure n over L of L over k. Okay, so now what I'm going to do, so to prove separability, we're going to count. Okay, so let's let I from k into n be the inclusion mapping. Right, so it behaves as the identity on every element of k, right, and it just puts it inside n. So now we have that alpha 1 is separable over k, right? That was that part about, so this is getting the process started. That was the thing that I wrote in the parentheses right here. And well, okay, I got to use I. So I of m sub alpha 1. I guess I'd better start double subscripting, huh? Yeah, alpha 1k. That's just m sub alpha 1. This is equal to m sub alpha 1k. Splits over n. So now, oh, and I got a typo in my notes. Let me just fix that real quick. Sorry. So this is by our previous theorem. So this is 4.2. So by theorem 4.2, there are exactly degree of k adjoint alpha 1 over k extensions of I, let's say extensions, now we're going to go from k adjoint alpha 1 into n of I. And now let's just pick one of them. I'm going to call it J. So let's fix an extension, little j, from k adjoint alpha 1 to n of little I. Now, now if you think about, so now we're going to move on to alpha 2, so then the minimal polynomial of alpha 2 with respect to k adjoint alpha 1 divides the minimal polynomial of alpha 2 with respect to k. And so j of the minimal polynomial of alpha 2 with respect to k alpha 1 divides j of the minimal polynomial of alpha 2 with respect to k. Now think about this. So j, because j is an extension of I, j fixes k. And so since j of m alpha 2k is equal to m alpha 2k, which we know splits over n, so which splits over n, so does, okay, so does J of M2, M alpha 2 K adjoint alpha 1. There's a lot of subscripts, a lot of, yeah, just keep your head straight. Okay, so now, what's our assumption in the theorem? So since alpha 2 is separable over K adjoint alpha 1, now we can count again. So this is one second. Oh, another typo in my notes. I kept writing 5.2. Should be 4.2. So by theorem 4.2. There are K adjoint alpha 1 comma alpha 2 over K adjoint alpha 1 extensions of, or extensions K adjoint alpha 1 comma alpha 2 into N why did I put an L there? That's weird. That should be an N. Sorry. One more typo. I think. Yeah. Sorry. I got one more typo in my notes. I wrote an L when I should have written an N. Okay. So extensions into N of J. All right, so now what do we have? We have this many extensions of I. And so we picked one of them. So J is an extension, or each of those J's. And then for each of the J's, we get this many extensions. So if you combine those two, so combining, we have, well, okay, I'm just going to throw the tower law at it. So it's going to be K adjoint alpha 1, alpha 2 over K extensions. So now we're going to be going from K adjoint alpha 1, alpha 2 into N of I. Right? For each of the extensions J of I, we get this many extensions of J. Multiply those, that gives us the number of extensions of I. And then we can keep repeating this process. So repeating this process, right? And we've seen this. What's the idea, right? So it's just the idea that the minimal polynomial of the bigger, or with respect to the bigger field, always divides the minimal polynomial with respect to the smaller field. That's just an ideal argument. So repeating this process gives us, so it'll be L over K extensions. So these are going to be maps from L into N of I. Okay, now we need to remember our previous theorem, which says if it's separable and the inclusion or the embedding, I guess the I of the minimal polynomial splits, then you have exactly a certain number of extensions. Otherwise, there are strictly fewer. So remember that final sentence. So now, by theorem 4.3, if L over K is not separable, this is the otherwise part, then there are, let's put it here, strictly less than L, degree of L over K extensions of I. But what do we say here? We have exactly that many, right? So therefore, right, since we have this many extensions, we can conclude that this had to be separable, because if not, we would have strictly fewer. So therefore, L over K is separable. Okay. Now, the wording of that, right? I mean, if you remember that corollary, it said that each alpha I had to be separable over K adjoin alpha 1 up through alpha I minus 1. It's kind of a pain to apply. We'll use it sometimes, but we're going to get a sort of a cleaner statement now, a corollary. That's, I don't know, somehow nicer to picture at least. So our next corollary, this is 4.5. If L, which is K adjoin alpha 1 up through alpha n, is a finite extension, and each alpha I is separable. So here's the good part, separable over K. We don't have to do K adjoin alpha 1 up through alpha I, right? Then L over K is separable. And the proof's pretty quick. We're just going to make use of our previous corollary. So first, we're just going to look at the splitting field for each of these alpha i's over K. Let's call it sigma sub I. So let's let sigma sub I be the splitting field for m sub alpha m sub alpha I over K. Now, since, and I guess, I mean, just because I guess let's put a little sub K there, so it's the minimal polynomial with coefficients in K. So since the minimal polynomial of alpha I with coefficients in K adjoin alpha 1 up through alpha I minus 1 divides the minimal polynomial of alpha I with respect to K, what that tells us is, this polynomial, right, each of these polynomials is separable, right, because we assume that each alpha I is separable. So, and m alpha I over K splits into distinct linear factors. Over sigma sub I, so does m sub alpha I with respect to K adjoin alpha 1 through alpha I minus 1. In other words, so what is that saying? It's saying that each of these alpha i's is separable over K adjoin alpha 1 up through alpha I minus 1. Right, and then we can just throw or apply our previous corollary. So let's say, in other words, alpha I, each alpha I, is separable over K adjoin alpha 1 up through alpha I minus 1. So now, apply. Corollary 4.4. All right. We got 2 more results that we need. And they're both, so this next one, this is corollary 4.6. So if f in k bracket x is separable over k, and sigma is the splitting field for f over k, then sigma over k is separable. All right, so the splitting field for a separable polynomial yields a separable extension. And the proof basically boils down to thinking about what sigma has to look like. Well, sigma is k adjoin all the roots of f. So, since sigma equals k adjoin alpha 1 up through alpha n, so it's that, and where these are the roots, let me say who these are. So where alpha 1 up through alpha n are the roots of f. And m sub alpha I divides f in sigma bracket x. Sorry, now I lost my train of thought. Right. Each m sub alpha I is separable over k. All right. If f doesn't have repeated roots, then divisors can't have repeated roots either. And so, so each minimal polynomial is separable. That tells us that each alpha I is separable. So sigma is formed by adjoining a finite number of alphas, where each of the alphas is separable over k. Now we can apply our previous corollary. So now apply corollary 4.5. Okay, and then this really is, and I think this is a theorem, not a nope, it's corollary. Corollary 4.7. So let's let L over K be a finite extension, be finite, and suppose that we have some field in between, so some m in between K and L. Oh, that should be a K right there. Now, if K over M and L over M over K and L over M, is that what I want? Yeah. So if M over K and L over M are separable, then L over K is separable. So remember last time what we had was if we know L over K is separable, then we know K over M and L over M are separable. This is sort of going the opposite direction, right? So now it's saying if you know that this one and this one are separable, then you can show that the big one is separable. Okay, and this one's, it's a little, it gets a little technical here. You just got to be careful with the details. So let's just keep our head straight here. So let's see now. Everything's finite here, and so we can build M by adjoining some stuff to K. Then we can build L by adjoining some stuff from L to M. So and I need to just keep this straight. So let's let alpha 1 up through alpha L in capital M be such that M equals K adjoin alpha 1 up through alpha sub little l, and let's let alpha L plus 1 up through alpha N in L be such that L equals M adjoin alpha L plus 1 up through alpha N. Now, we know that M over K is separable, so that tells us that each of these alphas here are separable over K. Right, so since M over K is separable, each, or say it like this, alpha I is separable over K for each, and now we have to keep track of which subscripts we're working with for each one less than or equal to I, less than or equal to L. Right, now just using the same idea, so it follows that alpha I is separable over K adjoin alpha 1 up through alpha I minus 1. Why is that? Because the minimal polynomial with respect to the bigger field divides the minimal polynomial with respect to K. Okay. So now we also have, so we'll say now, M, which equals K adjoin alpha 1 up through alpha L, is contained in K adjoin alpha 1 up through alpha L plus 1. I think I just need to go to L plus 1, right? Right, which is contained in L. Now, we've assumed that L over M is separable, And then remember, that tells us that we can do separability with the intermediate stuff. In particular, this field is separable over this one. Or the extension is separable. So since L over M is separable, so is K. Wait, what? Right, yeah. So is K adjoin alpha 1 up through alpha L plus 1 over K adjoin alpha 1 up through alpha L. So this is by theorem, that's theorem, where'd it go? Oh, 4.1. In particular, that tells us that alpha L plus 1 is separable over K adjoin alpha 1 up through alpha L. And then you can keep doing this process by just, one by one, right? You can change this to an L plus 1 and this an L plus 2 and get that alpha L plus 2 is separable over K adjoin alpha 1 up through alpha L plus 1 and so on. So we'll just say repeating this, we get that alpha I is separable over K adjoin alpha 1 up through alpha I minus 1 for all 1 less than or equal to I less than or equal to N. Now we can go all the way up through N. And now apply a corollary. This was 4. I keep writing 5s here. 4.4. So, alright, so now apply corollary 4.4. That tells us then that L over K is separable. So that's it. Tomorrow we're going to give you, or next time, we're going to get a definition, right, with the word Galois in it. So we'll see you soon.